Hello, in this video I'm going to run through what are commonly known as fictitious forces. So these are forces that look like they're acting upon an object or a system of objects, but actually they're just an illusion created by forces that are acting on us as the observer, not acting on the objects that we're observing. So this comes back to, if you think of when we started in all of this with our Newton's laws of motion, we've been talking about observing in inertial frames of reference. So these are non-accelerating frames of reference. If we move into a non-inertial frame, so a frame which isn't just fit into that Newton's first law definition of inertia, as in we're just moving along without a force acting on us, so we're either at rest or moving at a constant velocity. So we're in a non-inertial frame. That means as an accelerating observer, a non-inertial observer, we've got forces acting upon us. If we make the assumption that we are actually inertial when we're non-inertial, then we transfer those forces onto the objects that we're observing. It looks as though it's those objects that are experiencing the forces when actually we are as the observers. So the main two, which are the ones I'm going to look at in this video, are centrifugal force and the Coriolis effect. A good first step into looking at centrifugal forces is thinking of what happens as we go around a corner in a car. So say we were driving round and round in circles in a car, but we started off maybe going on a straight road and then the road curves off to the left. So as we turn the car to the left, it feels as though we're being thrown to the right. We'll hit the right hand side, our bodies will lean to the right as we turn to the left. So it feels as though we're being thrown outwards of the circle. If we kept going round and round in a circle here, at all points we're going to be leaning outwards from the circle, whereas all of our analysis of circular motion says that we must have a centripetal force which is acting towards the center for us to go in a circle. But our experience inside the car is that we've got a centrifugal force which is throwing us outwards. So what's going on with all of this? Right, so this really is, again, it's a frame of reference thing. That's what all of these things are, is what is our frame of reference. So sitting inside the car, which we've got to remember, inside the car is a non-inertial frame of reference because the car is accelerating. So let's say we were looking at a rear view mirror which has got an air freshener hanging off of it. So as we're going in a straight line, that air freshener is just hanging straight down. We turn to the left, so the rear view mirror attached to the car will automatically move with the car. The car, the friction on the road that's applied between the road and the tyres, that is what's giving the centripetal force to the car so it can turn in a circle. That friction is transferred all the way through the rigid structure of the car. So the rear view mirror is going to experience a force towards the center of the circle if we're turning off to the left, and it will instantly start moving. Now the air freshener, which is hanging straight down here, that doesn't have, because it's not on a rigid construction, it doesn't have a centripetal force immediately available to it. So as the rear view mirror attached to the whole of the car moves off to the left, the air freshener is going to keep going in a straight line. So we're going to end up getting this situation where the top of the string, because it's attached to the rear view mirror, has moved to the left, but the bottom of the string hasn't. It's been carrying on in a straight line. This then creates an angle on the string, which is giving us, so the tension in the string is then going to give us a component of force towards the center of the circle. So that's where our centripetal force is coming from for the air freshener. It's coming from this component of the tension of the string towards the center of the circle. Right, now we can look at what's happened here in two frames of reference. In the frame of reference of the car, which is the same as the frame of reference of the rear view mirror, the rear view mirror is considered to be fixed, and now the air freshener has moved to the right. But we know that the rear view mirror is in a non-inertial frame of reference. So that's our non-inertial, our accelerating frame of reference, which is our frame of reference as the observer. So in a non-inertial frame, the air freshener has moved to the right. If we look at it in terms of the road, so if we're carried on a straight road, and that was our frame of reference, then our rear view mirror is moving along, and it's moved round the corner off to the left. That's fine. The air freshener hasn't moved quite as quickly. It's hanging straight down there, and it's hanging off to the side when we're over here because it needs that component of the tension, but it's still moved to the left with respect to the road, with respect to the straight line of the road. So if we're in the inertial reference frame of the road, the air freshener has actually moved to the left, just not quite as quickly as the rear view mirror has. So which direction the air freshener has moved in depends on which frame of reference we're using. If we're in the inertial frame of reference, we've got a centripetal force, which is acting towards the center of the circle. If we're in the non-inertial frame, then we've got a centrifugal force, which is acting away from the center of the circle. So it's an illusion that's happening here. We're treating this non-inertial frame as being inertial, and then we're transferring that force, saying, well, if we're not experiencing that force, it must be the air freshener's experiencing it. If we're not experiencing a force to the left, then the air freshener must be experiencing a force to the right, where in reality, everything's experiencing a force to the left. So we need to take that into account. So this is why it's dangerous to use Newton's laws in non-inertial frames, because if you do, you start making up forces that don't exist. They just look as though they exist. Right, this is then the basic principle of what's going on in a centrifuge. It's the same thing that's happening here. If you've got a test tube of some, lots of particles floating around in a liquid, so all these things are dotted around in there. If you just leave it standing up for a while, eventually the effect of gravity is stuff will settle out over time. It might take a very, very, very long time, but these particles will probably settle out at the bottom. You could have some things that stay in suspension forever, I'd imagine, but eventually these are going to settle out. If you can increase the effective gravity, which is what a centrifuge is trying to do, then these things will settle out a lot quicker. So what forces have we got in play here? For one particular speck of one particle floating around in this liquid, we've got buoyancy, which I've hopefully spelt correctly. I always get the letters the wrong way around on here, but yeah, it looks right. So we've got buoyancy, which is keeping it afloat because it's displacing its volume in the liquid. So we're going to get a buoyancy force, which is going upwards. And we've also got friction, because if it's trying to fall downwards, we're going to have friction opposing the motion. So what's the difference in these forces from particle to particle? So if you've got a dense particle, so two particles of the same mass, say, the more dense particle is going to have less buoyancy because it's got a smaller volume, so it's displacing a smaller amount of liquid, so you're going to have less upthrust. So for the dense particle, we're going to have less buoyancy, and we'll also have lower friction because it's going to have a lower surface area, and the friction is going to depend on the lower surface area. So we've got less upwards force on the dense particle. So the dense particle is going to fall more quickly as it is. Now, if we start spinning round, so we take this tube, we attach it to a spinny thing in a centrifuge. So we've just got, some axis here which is spinning round horizontally. We've attached our tube on it, so the tube is sort of getting thrown out to the side. We need to have a centripetal force acting on everything here. So the tube attached is all rigidly attached to this central bar that's spinning round, so the tube's fine. But the particles that are inside the liquid here, well, the amount of centripetal force they're going to get varies with the density of the particle, and the more centripetal force that you've got, the closer you can stay to the center of the centrifuge. If you're going to move in a tight circle, you need a stronger force. If you've got a weaker force, it's going to move further out. So that's how it's separating these things out, that the more dense particles, because they've got lower forces acting on them, they're going to have a smaller centripetal force, so they will be moving outwards relative to the less dense particles. So we're going to get the dense stuff at the bottom and the less dense stuff at the top. But this is just a relative outward motion. Everything has still got a centripetal force on it. But if you analysed it in the frame of reference of the test tube, then it would look as though some particles are moving outwards and some particles are moving inwards. It's the air freshener all over again. So that's what's happening in a centrifuge. That brings us on to the Coriolis effect, which if you've heard of it, you'd have heard it in terms of weather systems, I would imagine, because this is giving us an explanation of why hurricanes rotate in one direction in the northern hemisphere and another direction in the southern hemisphere. So this is having a rotating frame of reference, as in the Earth. So these are really hard to draw, so let's see how I get on with those. Let's look at say we were looking at the Earth North Pole in the middle here. So we're looking at the northern hemisphere rotating round in this particular direction. So we've got an anti-clockwise rotation going on. This is our North Pole in the middle. And we're standing, say, as an observer on the edge here. Say we're on the equator. So we're moving round in an anti-clockwise circle. Yeah, if we had a point that we were rolling from, well, let's say starting from the North Pole first of all. So we've got something that we're going to roll down in a straight line from the North Pole down this circle towards the outside. I mean, I know it's a hemisphere, but the effect is exactly the same. So as this rolls straight down here, of course, the observer, we're moving around. So by the time we've got to this point over here, it looks as though the ball that we've rolled down has moved off to the left. It looks as though the ball was sort of rolled in a curve in order to get to the circumference of the circle, because as far as we're concerned, we haven't moved. I mean, I know we have moved from here round to here, but if we're going to make ourselves the frame of reference, then we've stayed in one place and the ball was curved off to the left. We can have the same thing if we were rolling it in a different direction. So if we were going to think of starting the ball on the outside and rolling it towards the center, well, once again, we've moved off to the side. It looks as though the ball is going to head off in this left-hand direction because we're moving to the side, but we're considering ourselves to be fixed. So if we've moved off to the right and the ball's gone in a straight line, but we consider ourselves to be fixed, well, the ball must have gone to the left to counteract us having gone to the right. So it's like centrifuge all over again. So it looks as though the ball will move in this sort of curving path. So it's in the same curve that we're taking this in a clockwise direction. These paths look as though they're bending to the right. It looks as though on this green line that the ball has curved to the right. On the blue line, from the point of view of the ball, it looks as though it's curved off to the right again. So yeah, it looks as though all of these paths here are curved in the right-hand direction. If we put all of this together, that we've got all of these points are moving around in the atmosphere, that you've got the air moving towards a point of low pressure, then it's going to look as though, say we've got these 4 points here, and we've got this low pressure in the middle, but all of the paths look as though they're curving to the right. So this one will look as though it's moving that way, this one will look as though it's moving that way, and so on, because as we've seen, it looks as though whichever way we're going, the ball curves in the right-hand direction. So if we've got wind moving around this low pressure here, it's going to follow the direction of the arrows, and all of those arrows are going anti-clockwise for the point of view of the hurricane in the middle. So everything's bending off to the right here for the green lines, but in terms of the hurricane that's going to form in between all of those green lines, you can see it's all pushing the air around into a circle which is moving anti-clockwise. You're going to get exactly the opposite thing happening if you look in the southern hemisphere, because the setup is exactly the same, except rather than our rotation here being anti-clockwise, we've now got a clockwise rotation. So all of the paths are going to be in a different direction. So now our 4 points, when we put them together, are all going the other way. So they all look as though they're bending off to the left rather than to the right. So the hurricane that we're going to then have in the southern hemisphere, well, all of those arrows are pointing in a different direction around the low pressure. So in the northern hemisphere, we're going to get anti-clockwise movement of air around the low pressure, and in the southern hemisphere, we're going to get clockwise rotation of the air around the low pressure. So it's all about, in this case, standing in a rotating frame of reference for the Coriolis effect. They're quite awkward ones to draw out, but this is something that you can actually play around with. If you get a spinning disc and start rolling balls across it, or go on well, I suppose you don't really get many roundabouts nowadays in playgrounds and such like. But it used to be quite easy to try these things out because there would be roundabouts everywhere, and you can try actually experiencing this firsthand. But yeah, if you think of these paths, it all makes sense. Everything bending off in a particular direction, because once again, we're moving as an observer, but we're considering ourselves to be fixed in space, which is exactly the same as we had when we went round the corner in a car. We're actually moving in a circle, but we're considering ourselves to be fixed, and then that throws that confusion. Well, where do we put that force in order to balance it out? Well, we throw it on another object, even though it's not acting on it. Same thing going on here. The air is moving in a straight line, but not relative to the rotation of the Earth. So they're the main two fictitious forces that we see. Centrifugal force, Coriolis effect. I mean, strictly speaking, everything that we're going to measure when we're on the Earth, well, it is a non-inertial frame of reference. It is rotating. We do have a centripetal force acting on us all the time. So all of our frames of reference that we're setting up are going to be non-inertial frames. For most situations, that isn't going to have any effect. I mean, it's a tiny effect, which is swamped by the reality of what we're trying to measure. It shows up on the scale of hurricanes. The rotation we're getting from the Earth. You get that myth that goes around that this shows up in the way water goes down a plug hole, and how it's different in northern and southern hemisphere, where it doesn't show up on that scale because the effect is too small. It shows up on large scale, but not small scale like that. But it's more of an effect if we're in a car going around a corner. That's a much stronger force that we're getting going on there. It's a much greater acceleration, I should say. of that's going to affect our observations. So we need to take into account these things when we're setting up a frame of reference. If we are in a non-inertial frame, how much does it actually matter? So yeah, worth keeping that in mind.